Hello guys, how things are going? This is Akash and today I'll talk about Transmon qubit coupled with environment and how to solve it using Quantum Monte Carlo method. So let's start with an overview. So first thing first, introduction, where I'll basically talk about qubits and then I will talk about the Transmon qubit, which is one specific physical realization of a qubit, and also about cavity. Then I'll talk about Jaynes-Cumming model, which is basically coupling between qubit and cavity and how it tells us about the uh, oscillations between excited and ground state of the qubit. Then I will basically do the comparison between my code and what I've gotten by using one specific module, which is known as qtip. Then I'll talk about open system, where I have coupled my Transmon qubit now to many modes of the environment and how I can solve it using quantum Monte Carlo method, which is also known as quantum trajectory. So then I will conclude. Alright, so let's begin with our talk. So first thing, introduction. What is qubit? So any quantum system which has two states can be represented as qubit. So sometimes you can also think of it as 0 and 1 state, and both of them are basically superimposed. So superposition of these two states, we can think of it as qubit, and you can also think of it in terms of a block sphere that you can see here on the right side of the screen. So any points on the surface of this sphere is one of the state of our qubit. So basically, if you think of any vector that depends on theta and phi, that gives us a unique superposition of 0 and 1 state. And you can also represent that in terms of this mathematical equation that you can see here, which depends on theta and phi. So that basically tells us in which direction the vector is in our block sphere. Alright, so as I told you, there are many different physical realization of a qubit. One particular is superconducting qubit, and there are many other which some of them I have listed here. Second is ion trap qubit, then third is NMR, which is nuclear magnetic resonance qubit. So for my talk here, I'll talk about one specific type of superconducting qubit that is known as Transmon qubit. Alright, so let me just show you the Hamiltonians of the Transmon qubit and the cavity. Alright, so if you see over here on the figures, what you see here in the figure B is so that is this cross sign with a box around it. So that is basically our Josephson junction, which is connected to the capacitor. So these two things together basically gives us the Transmon qubit. And if you want to think of it in terms of a Hamiltonian, you can see it here in the first equation. Alright, sometimes people also call it n-harmonic oscillator, which I'll just talk about it in a few minutes. And then there is another term that is the Hamiltonian for the cavity or a resonator. If you look at the Hamiltonian of it, it reminds you of the simple harmonic oscillator. So that's what it is. And if you look at the potential of both of these Hamiltonians, the dashed blue curve that you see, that is obviously for the simple harmonic oscillator or cavity. And if you look at the black curve here, that is for the Transmon. And one specific thing that you can see over here is that the energy difference between levels is changing as you go higher. So that's the reason we call it n-harmonic oscillator. Alright, so these two potential basically tells us the difference between the Transmon and the cavity. One more thing that you should know about the Transmon qubit is that this term EC and EJ. So these two variables basically tells us that how sensitive our qubit is to the charge noise. So if you look at this figure at the bottom, so Ng is basically a charge that is biased, that we have biased with our qubit. Alright, so if there are any fluctuations that are happening in the charge, so based on the dispersion of our energy levels with respect to the charge, we will see that how much influence this charge noise has on our qubit. So if we increase the EJ by EC term, as we go higher, this dispersion goes more and more flat, and we basically don't see any influence of the charge noise, so which is one of the interesting characteristic of Transmon qubit. Right? So next, what I'll do is basically I'll couple this cavity and the Transmon qubit, and we'll try to see what our model predicts, and then I'll show you how my code is also giving the same results. So let's start with Jaynes-Cumming model. Over here, I've shown the Hamiltonian HJC. So first two terms are basically the Hamiltonians of cavity and the Transmon, and the last term is the coupling term between between cavity and the Transmon. All right. So when we talk about Transmon, we only want to talk about the lowest two energy levels, because that's what we need for the qubit. So we will basically reduce the Hamiltonian of the Transmon to this particular h hat omega q b dagger p. All right, and this is how it would look like if you look at this figure. On the right side, we have our Transmon. On the left side, we have the LC oscillator, which basically represents our cavity. So normally in the model, we use 3D cavities, and we can, since it's also a harmonic oscillator kind of, we can represent it basically in this type of circuit. All right, and both of them are coupled by capacitor. So if we look at the energy levels and how it's changing, if we before the coupling and after the coupling, so that's what this figure is telling us about. So before the coupling, basically this 0, 1, 2, 3, it's telling us how many photons are there in our 3D cavity, and this up and down tells us about the either our Transmon is in the ground state or the excited state. So downspin basically tells us that it is in the ground state, and upspin tells us that it is in the excited state. So before the coupling, if you look at here, so and if we think of the energy difference between the Transmon level, which is omega q, and the frequency of our oscillator, the fundamental frequency, which is omega, if both of them are same, then we can say that either one photon inside the cavity and Transmon in the ground state, it has same energy level as 0 photon in the cavity and our Transmon in the excited level, right? So that is basically that state is degenerate. But if we couple it, these two together, then basically what happens is that this level becomes non-degenerate. And if we let it evolve over the period of time, suppose that initially our system was in the basically our Transmon was in the excited state, and there was no photons in the cavity, then over the period of time, this model predicts that what we'll see is basically the oscillations between these two levels. The photon will get emitted, and it will go inside the cavity, and then it will be absorbed by the Transmon again, and our Transmon will go to the excited state. Again, it will emit the photon and go to ground state, and there will be one photon inside the cavity. So basically this oscillations happens, and let's see what our model predicts. So when the cavity frequency and the qubit frequency is same, this is what my code predicts. The oscillations happening, and that same thing also we get from the implementation using Qtip module. And if you look at both of these graphs plots, then you can see the oscillation frequency is nearly exactly same basically, and also this oscillations are happening between 1 and 2, and if you see over here in this one also, so this is where it's happening after the coupling between 1 and 2. So that also this plot shows nicely, right? So, and one more thing that is interesting is what happens if the cavity frequency and the qubit frequency is not same. That means that there is a detuning, the difference between them, the frequency, both of the frequency is not zero. Then what we'll see is if the excited state won't go completely to the ground state, and same thing also happens true for the ground state as well. So the probability basically oscillate, but it does not go completely zero for the excited state, and for the zero state it does not go all the way to the 100% or 1 probability. So these oscillations that we are seeing here between the excited and the ground state of the transmon, they are known as Rabi oscillations, or some people also call it Rabi oscillations. So this is for the single mode of the cavity. But what happens if we have many of these modes? Like, let's think of it as infinite number of modes, and now we are coupling our qubit with this infinite number of modes. Understand that. Let's think about transmon as a system. So if our transmon it is not connected or coupled with outside environment, then we can think of it as a closed system, which means that basically it evolves according to the Schrodinger equation and we can solve it. But if it is an open system, which means that it's connected or coupled with the environment, then basically it has this dissipative character, where if our system is excited, like if it is in the higher state, eventually it will dissipate into the ground state, or it will release the energy to the environment. So that's exactly what we want to investigate in our case. So basically because we can solve such kind of systems using Master's equation, where we basically think of this system in terms of a density matrix. And so initially we had transmon in the excited state, and in the end it goes to the ground state and over the period of time. So what happens in between these two states, we don't know exactly. So basically we lack the information that's happening in between. So we kind of think of it in terms of a mixed states, where like we basically give classical probabilities of being in the excited and being in the ground state, because of a lack of information that happens in between. And that happens because this lack of information is the result because of infinite number of modes that we cannot track, or the interactions that's happening between the environment and the system that we cannot track. And that's the result of getting this mixed states, or adding this mixed states, and that's how we solve the Master's equation. But what if we want to try another way, where we basically think of a wave function picture, basically which evolves over the period of time based on the interactions. So that's where our quantum jump comes in, where basically what happens is that if we think of one particular trajectory of our system, where it evolves over the period of time, and after some time it jumps to the ground state, and then it stays there for a long period of time. So this is basically a simple spontaneous decay phenomena, but in a quantum picture. All right, so that's what basically we want to implement in our simulation. So if we look at the Master's equation, so this is how it looks like. So this rho is the density matrix of our transmon qubit, and H effective is the Hamiltonian which is the non-Hermitian because of this imaginary number. And basically we have two different terms here. One is, as I told you, non-unitary evolution given by this first term. The second term here is the jump term. So so basically that's what we want to solve it basically in our quantum Monte Carlo wave function method. So how does this work? So let me show you that algorithm by using some animations here. So just to give you some better idea about it. So think about our Transmon, which is in an excited state, and it will probably decay sometime in future. Alright, and it will get detected by this detector over here. So if we get a click in our detector, that means that the Transmon has decayed and it has now eventually settled in the ground state. Alright, so so this is the initial step. So initially it was in the ground state, in the excited state, and we don't see any click at the bottom in our detector. So let's go to the next step. We evolve the system and still we are not getting any click. So we can say that our Transmon is still in the excited state. Next step, again same condition, still in the excited state because we are not getting any click, and now we get the click in the detector. What does that mean? Is that the Transmon has jumped from excited to the ground state, and so the next step will be like we won't get any click on our detector and the Transmon will stay in the ground state, right? So that's what we are seeing here. And so basically what you are seeing over here is the evolution of our Transmon wave function over the period of time. So either it stays and evolve stays in the excited state, and there is some probability of having a jump, and so after many such time iterations, at one point it will basically eventually jump to the ground state and it will stay there for a remaining time if there is no such excitations happening. So in this particular model we are basically trying to model the spontaneous emissions happening in our excited atom or excited Transmon. So if you want to simulate this in our code, so basically we have two operators that does that. So one is the non-Hermitian time evolution operator, which basically leaves the Transmon in the excited state as it is, which is given by this operator, and then there is a jump operator which tells us the probability of going from excited to the ground state. So and both of these operators has different probabilities, and that also depends on the wave function that we have. Right? So basically what we'll try to do is since both of these operators have different probabilities of happening, we will assign a random number and basically we'll decide which one of these we should choose, and based on that basically we'll get a trajectory, one single trajectory of this particular system, or the way it's processing over the period of time. So this is for the single trajectory. Now what we'll do is basically we'll try to add more and more such trajectories, and then we'll take the average over all these different trajectories or possible path that our system could have taken, and eventually that will give us the results that we get from the master's equation. So that's what basically I have implemented in my code. So if you look at this two plots that I have gotten from the code, what you are seeing over here is, so again the same model where the Transmon was initially in the excited state, and since it has been coupled with the environment, what happens to it over the period of time, and implemented it by using the code I have written and also from the Qtip module implementation, and both of basically gives very much same answer. And in both of this I will basically had the same initial conditions, and I got the answer. So the theoretical value was 2, and for both of this I got very much close to 2, with the uncertainty of around 5%, less than 5% actually. So for this one I got 1.92, and for this one I got 2.01. So yeah, Qtip implementation was a little bit better than my code, but still it was good enough. So next thing what I've done is basically, so now instead of just letting my Transmon decay, I have some external input as well, which is the basically I'm driving the Transmon at the resonance frequency. So what we have seen, which were basically the Rabi oscillations in Jaynes-Cumming model from the ground to the excited to the excited to ground. Now what we are seeing over here, since it has coupled with many infinite number of modes instead of just single mode of the cavity, what we see is over the period of time this Rabi oscillations decays, and then after some period of time we won't be able to distinguish between the excited and the ground state. So basically, being in the excited and the ground state, the probability of both of them is 50-50. So basically eventually we have lost the information to the environment, and we have no way to distinguish between the ground and the excited state. So this is what we call normally as a decoherence happened, and we have basically lost this quantum phenomena of our system, and it has become basically classical because we have lost the information. So that's what also I have tried to implement in my code, and this is what I'm getting. So what we have seen in our case is basically so how the system evolves if it is coupled to a single mode cavity in resonance, and we saw that it also matches with the prediction. Another thing is what happens at non-resonance. Basically, the cavity frequency and the Transmon frequencies are not same. So these Rabi oscillations that we saw, they are not. They are basically becomes very little faster, and also we don't see the full oscillations. Basically, it does not go completely from 0 to 1. So there will be still some probability left for being in 1. It does not vanishes completely to 0 probability. And next thing what we have seen, instead of just coupling single mode, we coupled many infinite numbers of modes, environmental modes, and we saw that instead of just Rabi oscillations, what we see is the decay of our Transmon to the ground state. No more oscillations. That also we saw from my code, the Qtip implementation. And then if we drive the system or our Transmon at some resonance frequency, then this Rabi oscillations that we were seeing, they will eventually die out and we will lose the coherence. So that was my talk on Transmon qubit and how we can realize some of the interesting quantum mechanics or quantum physics, and also some very advanced topics, and also how to implement it using Quantum Monte Carlo wavefunction method and understand it more better. Thank you for listening.